Hello, in this video I'm going to take a quick look at interactions between particles, or more specifically fundamental particles. These are the ones that we were talking about in the last video when we drew out the layout of the standard model. So why have we moved away from talking about forces as we did in classical mechanics to talking now about interactions between particles? Now, I know I haven't gone through all of the details of the properties of all these particles and what they all mean, but one thing we are going to be familiar with is that electrons are going to repel each other. So let's work on that example. You've got two particles, these two electrons, which have got the same electric charge. They're both negatively charged. So let's just stick with what we know at the moment, that these will repel each other. And the repulsion will get stronger as they get closer. So say we set these off moving towards each other, the repulsion is going to get more and more, and these may deflect off, something like that. I mean, they might move back a bit more towards themselves, but let's say they're taking this sort of glancing path and they're deflecting off to the side. So why are we not just saying, oh, as they get close, oh, we're getting this force, so the force on the right hand electron on the left hand one is going to push it off upwards, and vice versa, pushing the right hand one downwards? Why are we not talking about this anymore? Why are we talking about an interaction? And that is because at the microscopic level, at this quantum level that we're looking at, there is actually another particle involved. These are the gauge bosons that cropped up when we were going through the standard model. So for each interaction, each fundamental interaction, there's a different gauge boson or set of gauge bosons. So in this case, we're looking at the electromagnetic interaction, and the gauge boson, this is the sort of force carrier in inverted commas, is the photon, which we normally denote with a sort of gamma sign. And this is exchange. This is an exchange particle. So every time there's an electromagnetic interaction, you get an exchange of what we call a virtual particle. And I'll come back to that in a second, as to why we're calling it virtual. But this photon gets exchanged. So rather than describing this in the classical way of saying we've got these forces, you've actually got a particle which gets exchanged, which is a photon. It gets exchanged between the two electrons, and this photon is carrying energy, momentum, maybe other things for the other gauge bosons in other interactions, but it's conserving everything. Essentially, everything has to be conserved in this interaction. Charge has to be conserved, energy has to be conserved, momentum, all of these things have to be conserved. But we've now got three particles that are involved in this. So we need to capture this in the description if we're going to be describing things accurately. So we can't just say, oh yeah, well, we've got forces going on, because it's throwing the photon out of the picture, and we need that to be there to have an accurate description. So why are we calling this photon a virtual particle? And we know photons are real. I mean, light's made up of photons. We can literally see it, when it comes into our eyes. Well, I suppose mainly what we're meaning here by virtual particle is it can't escape this interaction. You're never going to see this photon. It's trapped inside this interaction between the two electrons. It's hidden away. This is like a sealed unit. So that's really what we're meaning by virtual particle. The photon does exist, but it's sealed inside the interaction. You've got similar things going on. If we had quarks, let's think of a neutron, which we're going to start looking at more closely later on. But a neutron is a collection of quarks. It's an up quark and two down quarks grouped together. And these quarks are held together by gluons. Interactions is the strong nuclear reaction. So this strong nuclear interaction, if I can get my words out, strong nuclear interaction, and the exchange particle there are gluons. and these are being exchanged in various ways between the quarks inside the neutron, similarly inside protons. So we need to capture all of this if we're going to describe it all properly. So this is why we're moving now to interactions. Now, at the lowest level, at this particle physics level, when we're dealing, everything's in quantum mechanics and such like, this is all probability based. There's loads of different ways these interactions can happen, and we'll get onto this more probably in the next video, or maybe the one after, whichever one I do on Feynman diagrams. And this is picking up on the probability based nature of all of this. There's loads of different ways it can happen. We don't really have any way of saying with a lot of interactions exactly what has happened. We can say what the likelihood of a particular type of interaction, a particular configuration of that interaction, we can say the likelihood of it happening. But that's what we're dealing with. But when you aggregate all of that up, it might be, it's one thing to say, oh yeah, this up quark and this down quark are interacting in some way that's probability based. But by the time you've aggregated that up into the neutron, then you've aggregated up neutrons and protons into an atom, then you've aggregated up atoms into a solid. All of that aggregation just makes it all more predictable. All the probabilities just sort of fade away, and then we can come back to our classical classical descriptions in terms of force, because things are much more predictable at the macroscopic level. So you get that transition then between having to talk about interactions and probabilities, and then you aggregate it up, and then we can talk about forces again. So we have to capture that detail, as I say, at the microscopic level. So that's why we're now talking about interactions. One thing to add on the end of this, because I think I've said about as much as I want to say about that at the moment, is non-interactions. Because one thing that can be confusing when you start reading up about quantum mechanics and particle physics is you come across Fermi-Dirac statistics and Bose-Einstein statistics. And it can be easy to think, oh yeah, well, this is how we describe how all of these fundamental particles behave. But these are for describing, and this might sound a little bit weird, non-interactions. Now, I know, and I think I said this in a previous video, I know that we haven't looked at ideal gases yet, but you might have done some work on ideal gases. So an ideal gas is a statistical way of modeling how a gas behaves. So we're not at the quantum level here because we're dealing with atoms and molecules. So it's still small, but big enough to have got away from a lot of the quantum stuff that causes us problems when we get down to fundamental particles. And we're saying, okay, we've got a gas of these atoms and molecules, so we've got loads of them in a big cloud, and they're bouncing around and they're doing whatever they're doing. And the assumptions that we have on this is that there's no interaction, there's no forces acting between these atoms and molecules, except when they actually hit each other. And the collisions are for a negligible amount of time compared to the times that they're not hitting things. So we're really reducing down and saying, well, really, the particles in this gas aren't interacting. And when they're not interacting, and you've got atoms and molecules in a gas, so this is ideal because we're assuming this lack of interaction amongst other things, then we say it's described by Maxwell-Boltzmann statistics. And that will be telling you things like the distribution of energy based on the temperature of the gas. So the temperature is giving us sort of the average energy. And you say, well, how is that energy if you take a specific atom or molecule inside the gas? What is its energy likely to be? Various other things. So these statistics, Maxwell, I missed out the Boltzmann. Maxwell-Boltzmann statistics. These are describing the distribution of various things inside this gas. Now, this description does not apply at the quantum level. So if you've got fermions, we've got an equivalent for Maxwell-Boltzmann statistics, which is the Fermi-Dirac statistics. But again, this is assuming that the fermions aren't interacting with each other. It's like an ideal gas of fermions, in which case you describe them with Fermi-Dirac statistics. Similarly for bosons, you've got a whole load of bosons that aren't interacting. Then we use the Bose-Einstein statistics. So we're not really going to say very much about those when we're going through these videos on particle physics and such like. But just be aware that they're different to the stuff that we're doing with the interactions and the gauge bosons and the Feynman diagrams and all of that. They're separate in terms of we're looking at interactions and non-interactions. So yeah, just beware that you don't want to get these things too muddled up in your mind. Obviously, the details of them are, very complicated. But yeah, just beware of that distinction. So yeah, that's probably enough to say here, I think. And then we'll look more at these interactions and how we can describe them pictorially and look at the probabilities associated with them by looking at Feynman diagrams.